Now we're going to count. All right. So, derivatives then. We were just talking here. They needed to be able to draw graphs of these horrible, icky equations like something like that over there. Couldn't do it unless they made a t-table and you sat there and subbed numbers in and you plotted points. I mean, you're literally think about how many points you'd have to plot to even have a clue, because we know from previous experience that this is a polynomial and it's going to be something that goes, roller coaster looking up and down. It's going to be a horrible thing to plot. So they were looking for a better way to figure out, okay, how do we at least know when the graph is going to go up, when is the graph going to go down? It'd be nice to be able to tell where the peaks and the valleys on the graph are going to be so they could get at least a rough idea of what the function looked like. So somebody said, well, hey, we know a whole lot about lines. How do we know when lines go up and lines go down? What about a line tells us it's going up or going down? It's slope. Yeah, they said if we could do lines and slope, we'd know where it's going up and down. So, but they said, how do we get lines involved? This is a curve. So, here's the theory behind it. If I put a point right here, and I draw a line tangent to the curve, what does it mean to be tangent to something? This is a geometry question. When you are tangent to a circle, you touch it in only one point. So, I'm trying to touch it in one point. And if I come up here to another point, and I draw a line tangent to the curve at that point. Okay, what do you notice about the slopes of all those lines? It's changing. But what kind of slope do they all have? Positive slopes or negative slopes?
Definitely positive.
They're all positive slopes. But then, look what happens when you're smack exactly on top of the curve. Your tangent line is going to be horizontal. What kind of slope does that have? 0. So when we were going up, the slopes were positive. When I'm right at the top, at the peak of the curve, slope is 0. And what's going to happen as I start to come down and draw tangent lines on this side of the curve? Now, what kind of slopes do you have? Negatives. So they said, hey, dude, if I could figure out the slope of the tangent lines everywhere, I'll know when the slopes are positive, my graph's going up. When I get to 0, that could be a peak or a valley. And then when it's negative, I know my graph's going down. So their goal was to find out what's the slope of a tangent line. Okay. But you got a problem. And I'm going to come over here at another point on this graph so we can work with it differently. I need another color here. I'm going to work on, for the moment, suppose I wanted to find the tangent line right here. We are going to call this point A. Right? I want to actually find the slope of the tangent line at point A. Okay. What did you all learn back in Algebra 1? What do you have to know to calculate slope? You have to know the change in y over the change in x. And so we know to find the change in y over the change in x, how many points did you need? 2. Guys, didn't you learn the good old slope formula, y minus y over x minus x? So that's what they wanted to do. They wanted to use the slope formula. So they needed 2 points on this function, and so they could create a tangent line. Well, okay. We know 1 point is the point we're trying to be tangent to. So we know we can use point A. So they needed coordinates for point A. So it's A over, how do you figure out how far up it is on the y-axis? Assuming they knew some equation for it, how would you find the y-coordinate? You sub it in there, don't you? So, since we're just doing any point, though, we're going to say it's f of A then. Whatever you get when you sub the point in there, that's going to be the y-coordinate. So there's that point. But here's your problem. We're doing a tangent line, and I'm going to attempt to do it. Ooh, that was not a good attempt. I'm going to attempt to do a tangent line here to this point. I need to know another point on that tangent line so that I can do y minus y over x minus x. Am I going to know another point on that tangent line? I'm not. So they said, no problem. I don't know another point on that tangent line. But I can figure out any point on the curve because I got the equation of the curve. So let's go out and see if we can find another point somewhere on the curves. And so they said we're going to approximate it. We're going to try to get close. Okay, what I'm about to pick, you all are going to go shoot out to lunch because it's too far out. But I have a reason for what I'm about to pick. I'm going to pick my other point over here. I'm calling this point X. Okay, and I am going to connect those 2 points with a line. Okay, could I calculate the slope between those 2 points? Yes, I could. Okay, what would the coordinates of this blue point be? It's x over, what's its y coordinate? F of x, yeah. So, okay, we could do the slope of that line. So, and then you're all going, but that's nowhere close to the tangent line. Don't worry, we'll fix the problem in a second.
All right.
So, just doing slope of that, if I went y minus y over x minus x, they usually do the right-hand one minus the left-hand one. So I would have f of x minus f of a, that's y minus y. If I subtract my x coordinates, it would be x minus a. That's slope. Now, that's not anywhere close to that tangent line, though. So if I said if I gave you guys a choice, where would you like to move point x so it would be better? Could I go, is there a better place instead of picking point x clear out here, would you guys have liked it in a better spot?
The x-axis spot when you went up, like up.
Up, what do you mean up, up, up? Like, you want to be here at the base of the curve? Is that good?
No.
Because that would be a tangent line down there.
Yeah.
I mean, that's getting better.
No, up.
But is there a better one yet?
The other way.
What do you mean the other way?
So that.
Where it hits the x-axis. Okay, so Michaela's wanting to pick, like, I'm running out of colors here. She's wanting to pick, like, this one. Well, that's better yet. What would be the absolute best we could get? Right down, but how do you know where right below it is? Because you don't know the equation of the tangent line. So how do you ever know where right below the tangent line is? Where else might you want it to be? Let me pull up a second. I should have in my calculus, definition of derivative. I have one that can draw this better than I can because it. Oh, that. Just give me the applet. Uh-oh. I think it just asked me if I wanted to load that applet. Hang on a sec. Come on. Minimum. All right. Okay, so since the technology won't work, we'll just go back to the by hand drawing. Notice what you were doing every time you guys told me to pick another x coordinate. You picked one here, then you picked one over here. What are those x coordinates doing?
Moving by intervals of.
They're getting closer to what?
0, 1, A.
A. Wouldn't your best tangent line occur if you could get those 2 points as close together as possible so they're almost the same point? Then it would be almost the same thing as the tangent line. Okay, so what do we know that lets us say, hey, I want x to get really, 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 really close to A? Ta-da! The limit, yes. Yes, we simply put a limit on it. Let x get really close to A, and they get so close together it's virtually the same point, and you have the slope of the tangent line. Now, I know you're going, who cares about the slope of a tangent line to a curve? You'd be amazed at all the things we can do with these derivatives. It's astronomical. So, one of the things that you have to learn is, of course, the lovely
What was the prefix?
meaning. What was what now?
Space.
Thank you.
Why is it astronomical then?
So, a derivative. I'm going to ask you this on the test. You have to write this. It's on your journal. I will ask you this over and over and over. I should say a derivative represents the slope of what? Yeah. We actually usually say of a line tangent to a curve at a given point. And you feel free to go out and ask any of my calc students that definition. If they can't tell you that definition, I want to know about it. It's on their semester test again next week, even though it was on their last semester test too. They have to be able, you have to understand what a derivative is telling you. And it's giving you the slope of a line that's tangent to a curve at a given point. You should say that 5 times daily, multiple times a day. Slope of a line tangent to a curve at a given point. Okay. Now, this is the part I think is a little funky myself. This looks like a formula, but this little formula we just found, they call it the definition of the derivative. So, when it says write the definition of the derivative, this little formula is the definition of the derivative. That's what a derivative represents. This is considered to be the definition. So, a little bit funky on that aspect.
So what's the actual definition for?
The word definition is the fact that it's the slope of a line tangent to a curve at a given point.
Yeah, I'm tired.
Now, symbols for the derivative. Because different mathematicians have worked on derivatives, there are lots of symbols for the derivative. You're going to learn a couple of them. If you're writing your function as f of x, then they will write the derivative as f prime of x. That's how that's read, f prime of x. So if you see that symbol, it means find the derivative. Okay. If you're writing your equation as y equals, there's 2 ways they write derivative. Sometimes they just write y prime to say, hey dude, do the derivative. Or the very commonly used notation, they write dy over dx. It means dy stands for the change in y over the change in x. It's actually based on slope, change in y over change in x. That notation, dy over dx, is original to, there was actually 2 men who created calculus. They both did it around the same time period in 2 different ways. One of them was Gottfried von Leibniz, and that is his notation, and we are still to this day using his notation. The other was Isaac Newton. His notation was wacky, crazy, and insanely complicated. We don't use it. Thank you. I'm almost at 14. Okay, so we need to work a problem by this lovely definition. And have a bright flash.
If you want,
And then I might tell you the shortcut.
4, 5,
Ooh,
6,
why are you counting?
7,
It's only on 13?
9, 14 minutes.
Ah! Shoot it now. Kaboom. It was writing a minute ago. Well, heckerdees. We're stopping the recording.